Hello everyone, and welcome to a video on solving for the discrete time Fourier transform, or DTFT, of a uniform window. I've sketched the uniform window here. I'm calling the uniform window h of n, and it's equal to 1 between n1 and n2 and 0 outside of that. The uniform window shows up in numerous filtering and spectral estimation applications within digital signal processing, so it's really important that we know how to calculate its DTFT quickly. So this video specifically solves for h of e to the j omega, which is the DTFT of h of n, which can be written as this infinite summation of h of n times e to the minus j omega n, where omega is the radian frequency variable. And at the end, we will have obtained a version of the expression useful for sketching both the magnitude of the DTFT and the phase of the DTFT. So I've just redrawn h of n on this slide and written out the equation for the discrete time Fourier transform. So substituting into this equation, we see this equation is an infinite summation, but we know this is only a finite length sequence. So we can simply sum from n1 to n2, and we're summing 1 because h of n is equal to 1 over that whole thing, times e to the minus j omega n. Now, in order to solve this summation, we'll make use of the geometric series, right? This is a geometric series, and we have a formula for the partial sum of a geometric series. So if we're summing alpha to the n from n1 to n2, this is the equation that we can use. So this easily fits into that formulation, right? Now, alpha is just 1 e to the minus j omega, and then we can use this formula directly. And when we do that, the result that we get is we get e to the minus j omega, that's alpha, raised to the n1, minus e to the minus j omega, raised to the n2 plus 1, over 1 minus e to the minus j omega. So that's a perfectly valid solution for h of e to the j omega, but it leaves us with the question, how do we sketch, say, the magnitude of this frequency response if we want that? This formula right here is not in a particularly easy form for sketching, so we have to rearrange this slightly to make it easier to sketch. Here's the equation that we're working with, copied from the previous slide. And so one question is to ask ourselves, can we make this numerator term and this denominator term look like the sine function? After all, this is the difference of two complex exponentials, so that's sort of similar to sine. So maybe I can rework this to get sine in the numerator and sine in the denominator, and that'll make it easier for me to sketch. Now, it takes going through this a few times before you see how to reform this equation into sine, but we'll go through it here, and then you'll get the general idea. So let's start with the denominator. So with the denominator, let's start down here. So one form in the denominator that would start to look like a sine would be e to the j omega over 2 minus e to the minus j omega over 2. That looks like the form that shows up in our equation for sine, if we know Euler's. But in order to get that, right, I have to pull out a term over here that's going to be e to the minus j omega over 2 in the denominator. And so you see, if we multiply this back through, multiply this by this, I get 1. Multiply this by this, I get e to the minus j omega. So I haven't changed the overall denominator. I've just pulled this term out. And that's going to lead to something that looks very similar to the numerator of sine of omega over 2. And so I can do something similar in the top. I'd have to be a little more creative about what I pull out in order to make the two terms equal. But let's see what I can do. So on the top here, I'm going to end up with e to the j omega n2 minus n1 plus 1 over 2 minus e to the minus j omega n2 minus n1 plus 1 over 2. And in order to get that out of the top, what I'm going to have is e to the minus j omega n2 plus n1 plus 1 over 2. Okay, so I've obviously worked through this before, so it's easy for me to just pull these terms out. But let's multiply them back through and see if this actually works, right? So if I multiply this by this term, right, I'm going to add the exponents. And if I add the exponents, the n2 term is going to go away, the 1 term is going to go away, and I'm just going to be left with e to the minus j omega n1 over 2 times e to the minus j omega n1 over 2, which is e to the minus j omega n1. Similarly, if I multiply this through here, I end up with this term. And so now maybe we can start to see how we can rearrange this whole thing. So we've got an equation. If we multiply all this back through, we get exactly what we started with. Now, though, this term, if we just, technically we would need to have a J2 term on top and a J2 term on bottom, so that this looks exactly like this over this looks like sine, and this over this looks like, or this over this looks like 1 over sine. So I can rewrite this whole thing as sine of omega times n2 minus n1 plus 1 over 2 over sine omega over 2. And then I have to combine these two terms here. Well, that's just going to add an omega 1/2 up here, which will get rid of the 1/2 there. So I'll just be left with e to the minus j omega, e to the minus j omega n1 plus n2 up here, multiplying that together. And all of that is h of e to the j omega. Okay, so I would argue if we multiply all this stuff back through, these two expressions are equivalent. And so this is actually going to simplify our sketching of this equation. So we've obtained the expression that we wanted for the Fourier transform of this uniform window here. And that's the expression I have on the left-hand side. And we notice that it's a function of sort of two of the parameters n1 and n2. Specifically, in this part of the numerator, we're looking at n2 minus n1 plus 1, right, over 2. Well, n2 minus n1 plus 1 is the length of this rectangular window, right? If n1 were 1 and n2 were 3, then that would span 1, 2, 3. That's a 3-point window, right? So that would be 3 minus 1 plus 1. That's a 3-point window, right? So this n2 minus n1 plus 1 is the length of the rectangular window, and we could call that L. And then over here we have this complex exponential, a phase term, that's a function of n1 plus n2 over 2, right? Well, n1 plus n2 over 2 is the midpoint between n1 and n2, right? Which may or may not be an integer. It depends on what n1 and n2 are equal to. It will either be an integer or halfway between two integers. And so anyway, so we know that the phase term is going to depend basically on the midpoint of this rectangular window, where it's located, and the sort of part of the frequency term in this numerator is going to be a function of the length of the window. So we've obtained the expression for h of e to the j omega that we wanted. It's in a form that we can use to easily sketch the magnitude of the frequency response and the phase of the frequency response, and we'll do that in a future video. Thanks for watching.